All right, let's talk a little bit about surface integrals. Why are we talking about surface integrals? Uh, I've alluded to this several times, and I just want to kind of draw the big picture before we carry on with this section. In Green's theorem, what you're doing is you've got some kind of area, right? This is in 2 dimensions. And what you're relating in Green's theorem is a double integral over the region to the line integral around the outside, right? The double integral over the interior D is somehow related to the line integral counterclockwise around the boundary. Well, need is a strong word, we want to lift this idea up to 3 dimensions. And now you've got some kind of 3-dimensional figure, and you want to relate a triple integral over the inside to a double integral over the surface. Now we've done double integrals, we've done line integrals, double integrals, and triple integrals. The last thing, the missing piece, is the surface integral. How do we do the surface integral so that we can build this this theorem in 3 dimensions, Green's theorem in 3 dimensions, essentially? That's what chapter or section 6.6 is going to do for us. So the first thing we need to do is understand how to describe surfaces parametrically. And you'll remember that when we were doing contour integrals or line integrals, we had to parameterize the curve through 2-dimensional space, and then we would build this line integral. We have to go through the same process with surface integrals. We have to parameterize the surface integrals and then build the integrals. Now, when you're parameterizing a surface integral, you're parameterizing a 2-dimensional kind of thing, right? Even though a surface might be sitting in 3 dimensions, in a sense, we can kind of stretch it and flatten it and put it on a plane, and therefore it's a 2-dimensional object, even though it's sitting in 3-dimensional space. That means it's going to need 2 parameters in order to be parameterized. Just like a curve needs 1 parameter t to be parameterized, a surface is going to require 2 parameters. In this book and in most books, the standard conventional pair of parameters is u and v. So we use u and v to parameterize surfaces. We're going to learn how to do that. We're going to keep it simple. Obviously, parameterizing complicated surfaces is complicated. We're going to be looking at surfaces that are cylindrical or conical in nature or spherical in nature, and we're going to take advantage of the cylindrical coordinate system transformations or the spherical coordinate system transformations to parameterize these somewhat simpler surfaces. So I'm not going to be asking you to parameterize really crazy kinds of surfaces, just surfaces that fit nicely within certain coordinate systems, either Cartesian, cylindrical, or spherical. Once we've figured out how to parameterize, then there's a really beautiful process that we go through with the parameterization to build the surface integral. And we'll see that in a minute. And you'll see that it actually relies on our knowledge of space curves that we picked up in chapter 3. The idea that the derivative of a space curve gives a tangent in that direction. We're going to do that. You're going to see that that idea emerges again here with surface integrals. Once we do that, we'll define a generic surface integral, the so-called scalar surface integral, and then we'll move on to computing fluxes in a vector version of the surface integral. I've already kind of hit on some of the big ideas, you know, how Green's theorem relates 2-dimensional integrals to 1-dimensional line integrals. Here we're generalizing to 3-dimensional the 3-dimensional situation where triple integrals over a volume are related to double integrals over the surface. Before we do that, we need to define what the surface integral is, and so on. All right, let's do a bit of a flyover of the textbook before we get into the exercises at the end. Parametric surfaces are the big thing. We see a very similar notation. a bold-faced R, but instead of bold-faced R of t describing a curve through space, we're now using a bold-faced R of two variables, u and v, that describes a surface sitting in 3 dimensions. And as u and v range over their parameter ranges, they fully describe the piece of the surface that we're interested in. Let's look at a very simple example. We want to parameterize a piece of a cylinder. We've got a cylinder here. What we do is we just, gosh, I don't know how big the cylinder is. It doesn't really say. But anyway, it looks like they're using R equals 1. So a cylinder radius 1 going along the z-axis. We can describe circles in planes parallel to the xy plane using cosine u sine u. And then we can describe, we can move those circles up and down along the surface. I see a typo here, I think. This u really should go from 0 to 2 pi, and then this v should go from minus infinity to infinity. And that would fully describe the circle. Sorry, the cylinder. Here we go. So it looks like they fixed the typo here. So a cylinder, a general cylinder of radius r. The horizontal cross sections are going to be circles of radius r cosine u, r sine u, and then v is going to move those circles up and down along the cylinder to trace out the entire object. All right, let's keep going here. Finding the parameterization is usually a matter of looking at the surface and trying to bring to bear either cylindrical coordinates, spherical coordinates, or maybe you even get to stay in Cartesian coordinates. We'll see examples of all of those in a bit. All right, so here are a few more examples. I'll let you trace through those. Now, something that's going to be important as we build the surface integral is imagine this parametric surface, and here's a line maybe traveling in the u direction. Here's a line traveling in the v direction in parameter space. If we take the derivative with respect to u and the derivative with respect to v of the parameterization, what we get are tangent vectors in the u direction and in the v direction. If we take the cross product of those tangent vectors, we get a normal vector, and if we take the magnitude of the cross product, what we get is the area of the parallelogram described by the two tangent vectors. It turns out that that parallelogram is a very good approximation of this tiny patch of surface. We're going to use this idea to patch together a surface integral. We're going to patch together a bunch of tiny little pieces of surface. We're going to compute the areas of those tiny little pieces of surface by taking the derivative of the parameterization in the u direction, in the v direction, taking the cross product, taking the magnitude of the cross product, and using that as an approximation of this little patch of area. And as we take the number of patches to infinity, make them smaller and smaller, that approximation becomes exact, and the surface integral becomes exact. Let me go back now to some notation here. A parameterization is regular if the cross product is non-zero in the entire domain. Also called smooth. So these two definitions are similar. There's just the same word for this, different words for the same idea. It's not super important. We just don't want this cross product to disappear a lot. So here, if it disappears at all, it's not a regular parameterization. It's not smooth. We're actually going to see an example where it does disappear, but only at a point, and we're going to find that that's actually okay. So a couple of vocabulary words here that are kind of important technically, but not in practice very, something that we run into very often. All right, so Surface area of a parametric surface, we're going to build this using integration. As I described, we're going to do the partial of the parameterization in the u direction, in the v direction, cross product, magnitude. That gets a little patch of area. We're going to sum up those little patches of area in an integral like this. And if we integrate over the parameter range d, we will get the area of the surface. This leads us to a definition of the surface integral. We start by, we have a function of 3 variables. This is the scalar surface integral. We can build this little Riemann sum, a double Riemann sum. And delta Sij is just the area of a little patch of surface times the function evaluated at a point on that little patch of surface. We sum up all of those little products. We let the number of patches go to infinity, and we end up with the scalar surface integral. To compute this surface integral, this is a symbolic object. It needs to be converted into something, a double integral that we can actually calculate. To do that, we end up parameterizing the surface and then computing the magnitude of RU cross RV. Let's walk through that for this particular example. Calculate the surface integral of this function times ds over the cylinder x squared plus y squared equals 4. Z goes from 0 to 3. So there's this little cylinder, and there's some function that we're integrating. It doesn't have any sort of physical meaning at the moment. It's just an abstract exercise. The first thing we need to do is parameterize the cylinder. The cylinder has radius 2, so in the x-coordinate and y-coordinate, we're going to see 2 cosine u, 2 sine u, and in the z-coordinate, we're just going to have a v going from 0 to 3. It's important to write down the parameter ranges that describe your parametric surface, because these are going to be the limits of integration when you do finally build that. Now, you compute RU and RV, and you write them here. You compute the cross product, and you get this. You take the magnitude of the cross product, and in this case it turns out to be 1. In most cases it's not so simple. It'll be more complicated than that. Now you go back to the surface integral. This surface integral becomes the integral over the parameter range, 0 to 2 pi, 0 to 3. The function evaluated on the parameterization, so everywhere I see an x in the function, x, I'm going to replace it with 2 cosine u, and y I'll replace with 2 sine u. That leads me to this integrand, and then I have the magnitude of RU cross RV. They use TU and TV. I use RU and RV. I don't know, it just makes more sense to me. That turns out to be 1, so not a big deal. And now you're just left with a regular old integral. Integrate with respect to u, 0 to 2 pi. With respect to v, 0 to 3, works out to 12 pi. All right. I'll let you read that again. Parameterize, build the integral, evaluate the integral. A scalar surface integral, the most common application is the mass of a sheet. So if we go back to our cylinder, we could pretend that this is some variable density cylinder, and the density function is at a particular point is x plus y squared. If we did that, then we would have density times a little piece of area. That would give us a little piece of mass, which we'd be summing up, and that would give us the mass of this little piece of surface. That is formalized here in, gosh, where is that formalized? Well, I don't see it here. Oh, calculating the mass of the sheet. That's formalized here and in the paragraph right above. So scalar surface integrals have several real-world applications. Computing the mass of a sheet with a given density is one of them. All right, let's move on to the vector version of a surface integral. Here you've got a surface and it's sitting in the presence of some vector field. Let me scroll down a little bit. Here's a surface and there's some vector field that's passing through it. And you want to understand the flux of the surface through the flux of the vector field through the surface. It's the same idea. We're going to parameterize the surface, and then we're going to find normals to the surface, dot it with the vector field, and then sum up across the entire surface. That turns out to have a nice form as well. So symbolically, it's the integral, the double integral over the surface, f dot ds. And be careful here. This is a d with a bold-faced s, and that suggests the vector version of the surface integral, which is equivalent to f dot n ds with a non-bold-faced s. This is the scalar surface integral that we learned earlier. How does this work? So you parameterize the surface, and then it's easy to compute n just by computing RU cross RV. And once you do that, this is the standard normal vector. You would normalize it. And what is the normalization? It's RU cross RV divided by the magnitude of RU cross RV. But lurking inside ds is another magnitude of RU cross RV, and they're going to cancel and just leave behind the very simple RU cross RV, which you will then dot with F and carry out the integration. So you can see that cancellation here, and you end up with this somewhat simpler version. So if you want to compute this flux integral over a surface, you can evaluate the vector field along the surface and just dot it with RU cross RV and do the integral. So let's look at this particular example. We want to compute f dot n ds, where f is this vector field, and the surface is given by this complicated expression. What are we going to do? We're going to compute RU and RV and take the cross product, and then we'll evaluate f along the surface R. We'll take the dot product. The parameter range is 0 to 4 in V, 0 to 3 in V and U. We'll do that integral, and we'll end up with this flux, 340, whatever that means. All right. Now, as you know, there is more than one normal vector, and if you're parameterizing and computing RU cross RV, you might end up with a normal vector that points this way on the surface, or you might end up with a normal vector that points this way on the surface. And you might say, hey Schuler, which one should I use? And the answer is, use the one they tell you to use. And you're always going to have to be told which normal vector to use. So you read the problem carefully, and you look for clues that suggest which normal vector to use. Now, worst case scenario, if you use this one instead of this one, all you're going to do is introduce a minus sign, and so you can go back after the fact and say, oh, this flux should have been positive, I got a negative, I did everything else right, I used the opposite normal vector, I'm just going to change the sign. So you don't have to do a massive recalculation to fix it, just change the sign. What are some things to look for when you're computing the direction? For example, this guy says calculate the surface integral like this, and it doesn't talk about orientation, and I think that's a flaw, right? It really should talk about orientation right off the bat. It gets into orientation a little bit. Where does it get into orientation? Up here a little bit. So you're either going to be told to use the outward normal like this, and that will let you pick the correct normal vector, or the inward normal, although that's rare. Or if it's an open surface, right, inward and outward only makes sense on closed surfaces, right? You point into the surface, you point out of the surface if it's closed. If it's an open surface, then you need to be told which direction. Often it'll be like the upward pointing normal. The upward pointing normal is the one with the positive z coordinate. Up is positive z. If that's not sort of appropriate for your geometric situation, it might say the normal that has positive y component. But always look for that information to orient the normal vector. Now, you might say, do all surfaces have an orientation? And the answer is no. Classic example is the Mobius strip. This is a non-orientable surface, and there are actually other non-orientable surfaces. Let me show you another one. I'm getting my Klein bottle, which some students gave me several years ago. This is a more complicated non-orientable surface. You can read about it on the web. Klein bottle, K-L-E-I-N bottle, and this is also a two-dimensional non-orientable surface. What that means is you can't do surface integrals on this. You just can't. They're not well defined. They don't really happen much in applications, so you don't have to worry about it, but it's a fun thing to think about, and it just goes to show you that surfaces are perhaps more complicated than you imagine. All right, let's do a few exercises here. Problem 278, a cone with base radius r and height h, where r and h are positive constants. We're asked to parameterize that surface. Let's do a quick sketch so that you understand what we're talking about here. So we're talking about a cone with a circular base and then going up to, say, the z-axis, a height h, and then this radius. I'm going to use big R instead of little r here because I'm going to eventually switch over to cylindrical coordinates, and I just want to avoid the confusion. So the radius of that base circle is r. All right, how do we parameterize this? Let's use cylindrical coordinates, and we see that the cross sections of this cone are circles, and essentially kind of depend on how far away from the origin you are. So if I just move a distance r away from the origin, I'm up here, and that gives me the z value. So what I want to do essentially to start out with is just relate z to r. And the way to do that is to find the equation of this line right here. So let's find the equation of that line. We'll write L as a function of, let's see, I should be consistent here. I want to use capital R, and we'll use little r. L as a function of little r, the distance from the origin. So let's put that here in what I call the RZ plane. And let's sketch in just a line that goes from 0h to R0. And we just want the equation of that line in the RZ plane. All right, let's compute the slope. We have 0 minus h over r minus 0. Let's put that into the point slope form, and let's use this point in the point slope form. So that gives me z is equal to minus h over r, x minus r. And not x, excuse me, but little r here. All right, so that's z as a function of r. Let's just double check. When r is equal to 0, you're here at the origin, and the height z is just h. And when r is equal to capital R, you're out here at the edge of the base, and z is equal to 0. All right, given this information, we're now ready to parameterize. We know that cross sections of this surface are going to look like circles in planes that are parallel to the xy plane. So we'll just parameterize that as u cosine v, u sine v, and that comes directly from what we know, right? This is a circle of radius u, and the angle that sort of controls the going around the circle is v. Now, how are u and v related to each other? Or in particular, sorry, how are z and u and v related to each other. So we need to figure out what's the z coordinate down here. And we've got that figured out. If u is the distance from the origin, then we know that we can figure out the z value by plugging u into the equation of the line. So z is equal to minus h over r, u minus r, like that. Z doesn't depend on v. This is radially symmetric, so we have it. We have the full z dependence. It's simply minus h over r, u minus r, and that finishes out the vector. Now, whenever you parameterize a surface in this section, it's really important that you also tell me what the parameter range is. So over what range of values can u vary? It can go from 0 out to capital R. And over what range of values can v vary? Remember, v is playing the role of the angle here, and it goes all the way around the z-axis. So that's going to be between 0 and 2 pi. And putting those together, that's a parameterization of the surface, which you could then go on and do surface integration with. Just to double check this, I've actually built a GeoGebra interactive that shows this parameterization. And it's got, trying to get my computer to wake up here. It's not happy. Let's see if it's awake over here. No. Let's see if I can just reload it. There we go. Okay, so here we see a cone. Here's me varying r between 0 and 5. And all that does is change the radius of the base. And then here's me changing h, the height of the thing. I introduce, or essentially GeoGebra lets me plot parametric surfaces. I give the 3 coordinates in terms of u and v, and then I say that the u parameter goes from 0 to r, and the v parameter goes from 0 to 2 pi. And all of that information comes together to give me this conical surface. And that just verifies that this parameterization is what I claim it to be. Okay, in the next exercise, we're asked to evaluate a scalar surface integral. So this is the most basic form of the surface integral. And what we need to do is examine the situation and parameterize the surface and evaluate the integral. I highlighted this last bit of text that says in the counterclockwise direction. That doesn't make any sense in this context. It's a typo. I've reported it to the textbook authors, so just ignore it. You read for the following exercises, S is the hemisphere, and evaluate each surface integral, period. Counterclockwise direction does not make sense. It actually, my guess is that this is a typo related to something that we'll learn about soon called Stokes' theorem, where there is an orientation that's clockwise or counterclockwise, but we'll cross that bridge when we come to it. Okay, remember how this works. In order to evaluate a surface integral, we first need to parameterize the surface. Now, this is a hemisphere. And the best way to parameterize surfaces that are sort of related to spheres is to use spherical coordinates. And that's because the sphericalness is kind of built into those coordinates, and we can take advantage of that. So if you were just thinking about this, if you were just trying to describe this hemisphere in spherical coordinates, we see this is a hemisphere of radius 2. You can imagine, right? If I'm on the surface, what's rho? Rho is going to be 2 because everywhere on this hemisphere I'm a distance of 2 units from the origin. So rho is a constant 2. Now, what is theta? Well, the hemisphere goes all the way around the z-axis. So theta is going to just go all the way around. Theta is going to go from 0 to 2 pi. And what's phi? What what are the possible angles that a point on the hemisphere will make with the z-axis? Well, they can go from 0 all the way down to pi over 2. Phi equals 0 down to phi equals pi over 2. So the spherical coordinate transformations are ideal for describing this piece of a sphere. We have in spherical coordinates, rho is equal to 2, theta is less than or equal to, sorry, is greater than or equal to 0 and less than or equal to 2 pi, and phi is between 0 and pi over 2. And remember that the spherical coordinate transformations look like this, that x is equal to rho cosine theta sine phi, y is equal to rho rho sine theta sine phi, and finally z is equal to rho cosine phi. And what do we have to do when we're parameterizing? We have to describe the x, y, and z coordinates of the parameterization in terms of two variables u and v. We can do that here. Rho is a constant, so we're going to get 2, and then we're going to let, playing the role of theta, we'll let that be u, and playing the role of phi, we'll let that be v. Just because the book uses u and v, and we want to try to be consistent when we're parameterizing surfaces, we'll try to always use u and v. Just like back when we were doing space curves, we always use the parameter t, or we often use the parameter t. So rho is the constant 2. We're going to use u for theta, so cosine of u, sine of v, for v is playing the role of phi. In the y coordinate of this parameterization, again, rho is 2, sine of u, sine of v. And the third component, the z component, is 2 cosine v, like that. Now remember how this works. We have to compute the cross product of RU and RV. So first we have to compute RU and RV, and this looks really scary. There's a lot of trig functions flying around here, and you might think, you know what, I'm just going to do this on Sage. But this is an example of where the computation looks terrible, but it's actually not as bad as you might imagine. And I think it's worth going through because you really begin to see how spherical coordinates make this problem easy. There are lots of ways to parameterize a sphere. You can do it in Cartesian, you can do it in cylindrical, you can do it in spherical. Spherical is the best choice, and you'll kind of see it here as we do the calculation. Let's compute the partial of r with respect to u, and pay attention to where the u's happen. They happen here, here, and nowhere else. So taking that partial derivative with respect to u, we get -2 sine u sine v, 2 cosine u sine v, and then the last component is 0 because there is no u in that last component. Let's do RV. So we want to take the partial of r with respect to v, and again, let me point out where the v's are. The v's are here, here, and here. So we'll be really careful. We'll take the partial of the first component with respect to v, that's 2 cosine u cosine v, 2 sine u cosine v, and last, -2 sine v. All right, now we've got RU and RV. We want to compute the cross product, RU cross RV. The first component is going to be 2 cosine u sine v times -2 sine v. That's going to be -4 cosine u sine squared v minus 0 times this term, which is 0. The middle term is going to be 4 sine u sine squared v with an extra minus sign because it's the j component. 4 sine u sine squared v. All right, and the last component looks like a mess, not too bad though. we're going to get 2 sine squared u sine v cosine v. Sorry, negative 2 sine squared u cosine v sine v minus, oh, and not 2, excuse me, but 4, minus 4 cosine squared u cosine v sine v. Now, let's start looking for simplifications. First of all, we see there's a simplification lurking here with the sine squared u and the cosine squared u. This is going to simplify to negative 4 cosine u sine squared v minus 4 sine u sine squared v. And last, let's see, negative 4 cosine v sine v. Now, of course, we need to take the magnitude of that result, so the magnitude of RU cross RV. Square these things, add them up, and take the square root. So we get 16 cosine squared u sine to the 4th v plus 16 sine squared u sine to the 4th v plus 16 cosine squared v sine squared v to the 1/2. Let me make a little bit more space for myself here. Alrighty. A couple more Pythagorean identities. Let me identify those for you. Here and here is a cosine squared u and a sine squared u. So those are going to collapse to 16 sine to the 4th v plus, oops, there's a 16 right there, not a 14, plus 16 cosine squared v sine squared v, all that to the 1/2. Now, do you see any other identities that we can apply? The answer is yes. This thing can be broken up into sine squared v sine squared v, and that sine squared along with this cosine squared is another Pythagorean identity. So you got to keep your eyes peeled for these things. They're everywhere, especially in spherical coordinates. When you're working in the right coordinate system, nice things happen. What's left behind is 16 sine squared v to the 1/2, and we can actually simplify that all the way down to 4 sine v. Now you might wonder, where's the absolute values? And I'll come back at you and I say, well, let's look at where v lives. V is between 0 and pi over 2, and the sign is positive from 0 to pi over 2, so we don't need absolute values. All right, so the magnitude of RU cross RV turns out to be, what looked really scary turns out to be a relatively simple expression, 4 sine V. Let's go back over to the surface integral now and see if we can't build it out. So the integral is now over the parameter range, 0 to pi over 2 in v, 0 to 2 pi in u. And then we take x minus 2y and express it in terms of the parameterization. X is 2 cosine u sine v minus 2y. Y is 2 sine u sine v. All right, and then all of that is multiplied by the magnitude of RU cross RV, which we determined was 4 sine V. And then we integrate with respect to V and then with respect to U. It turns out that this integral is separable. If you want to go ahead and break the integral up at this minus sign, so you have two separate double integrals, and then separate the u components and the v components, you can do this integral pretty easily. And what you'll find is if you do the u integration first, you're going to get zeros everywhere, and this thing kind of collapses to 0. So I'll leave that as for you as an exercise, but it turns out that this surface integral happens to be 0. All right, in the next example, we're asked to compute a flux integral. And this gets back to the example that I introduced way back at the beginning of the class and we keep revisiting. Now, the example I mentioned at the beginning of the semester is flux across in 2 dimensions. Now we know enough to be able to do flux in 3 dimensions. So you're asked to compute this surface integral. Another typo here, by the way, this should be a capital S, not a lowercase s. Again, I've reported it to the book authors. This is f dot n ds, and we know that this has a really nice form. We know that we can write this as the integral. Now let me switch back to black here. Integral of f dot ru cross rv d, gosh, I guess dA, where a is over the parameter values. So this would be over the parameter set. So all we have to do is parameterize this thing and then build the integral and execute it. All right, so S is the portion of the plane z equals y plus 1 that lies inside the cylinder x squared plus y squared equals 1. You know, this feels like a job for cylindrical coordinates. I want to describe the plane, this part of the plane inside the cylinder. And I'm just going to parameterize. I'm going to start with u cosine v, u sine v. And what that does is gives me a disk when u is between 0 and the diameter of the cylinder, or the radius of the cylinder. So u goes from 0 to 1. And v is playing the role of theta. It goes all the way around, 0 less than or equal to v less than or equal to 2 pi. All right, what that does is gives me a disk of radius 1 in the xy plane. What I really want to do is get it up onto the surface. The way to do that is to plug it into the equation for the plane, z equals y plus 1. That's just, what's y in this situation? Y is u sine v, u sine v plus 1. So that's what I get for z when I plug y into this equation. I get u sine v plus 1. All right, now we're off to the races again. We need to compute ru, rv, ru cross rv, and then build the integral. Let's do that. All right, so ru is the derivative with respect to u. Let's again just make sure we see where the u's are. All right, so that's cosine v, sine v, and sine v. Rv, let's see where the v's are here. There's a v, and there's a v. That's minus u sine v, u cosine v, and u cosine v. Now let's compute ru cross rv. In the first case, we get u cosine squared v. Sorry, not u cosine squared v. We get u sine v cosine v. You do have to keep your wits about you when you're doing these. Minus u cosine v sine v. That's a pleasantly simple result. That gives me 0. Let's do the middle component. In the middle component, we have u cosine squared v. And there's a minus sign because we're doing the middle component. Lots of minus signs going on here. We have u sine squared v with another minus sign. All right, looks like we're going to get some simplification there. And last, the third component, we get u cosine squared v. plus u sine squared v. Just going to check my notes here to make sure I haven't misled you. All right. The first component simplifies to 0. The second component simplifies to negative u, and the third component simplifies to u. Now, one thing that's lacking here is, and in fact, I guess this is another typo, which I haven't reported to the book. So many typos in this section. The outward normal vector. Remember I said you can't talk about outward pointing normals or inward pointing normals unless the surface that you're integrating over is a closed surface. This is not a closed surface. This is just a piece of a plane that's lying inside of a cylinder. All right, not a closed surface. So what does outward normal mean? Instead, what I'm going to do is change the problem so that we're working with the upward pointing normal. All right, so what do you do? How do you know whether this is the upward normal? Is this upward? Well, a vector is upward if its z component is positive. The z component here is a u, and the parameter range for the surface is 0 to 1. So this is unambiguously upward pointing all the time. So this happens to be already the right normal vector. We'll call it n, and we'll carry on. Now we're ready to build the integral. The limits of integration are over the parameter range. We'll do u first and then v, but it doesn't matter. And then we'll look at f dotted with n du dv. Well, we've got to figure out this f dot n thing. Now is when we bring in this part of the equation. And we need to evaluate f along the parameterization. All right, so f along the parameterization, let me just write this down here. F is x squared, y squared, z squared. And along the parameterization, which I'll say is just f of r, we are going to just have u squared cosine squared v, that's this part, the x, comma u squared sine squared v, that's just this part, the y, and then finally sine v plus 1 quantity squared in the third component. Now what do? We look at f evaluated at r dotted with this n that we found up here. 0 times this is 0, negative u times this is negative u cubed sine squared v, and then finally plus u sine v plus 1 quantity squared. That is fr dot n. Now we're ready to plug that in. So this is equal to the integral from 0 to 2 pi, integral from 0 to 1 of the integrand minus u cubed sine squared v plus u times the quantity sine v plus 1 squared du dv. And I took the liberty of plugging that into Sage, and surprisingly it comes out as pi. So after all that, the flux of this vector field across this piece of surface is in the direction of this normal vector is pi. Do I believe that it's positive? I don't know. I'd have to dig in a little bit more closely, but it does look like these vectors, for instance, are sort of acute with the normal vector, which is going to give me positive contribution. These vectors down here might be obtuse with respect to the normal vector, which would be negative, but they're also smaller than these vectors. And so I suspect that this is okay a positive pi seems reasonable here, or at least a positive value seems reasonable. All right, in the next example, we do one of the few applications of scalar surface integrals, and that is computing the density of some surface area with this weird density function. That is the Greek letter xi, xi, xi. I used to practice drawing that when I was in differential equations because that's where it comes up a lot, and I still am not very good at it. It looks like a little squiggly tornado or something. Anywho, all right, 288. So now we're building a surface integral. We're given the surface with z less than or equal to 1. What kind of surface is this? This is a paraboloid. So roughly speaking, it kind of looks parabolic, and then it's got these circular cross sections. And we have z less than or equal to 1, so it's the portion of the paraboloid sort of in between this plus or minus 1. What's a good way to parameterize this? You know, the circularity of this in directions parallel to the xy plane makes me think cylindrical again. So I'm going to parameterize this r of u and v as u cosine v, u sine v, and then what's the z component? It's just what you get by plugging these two in. That's going to work out to u squared. What's the parameter range? It looks like u is going to go from 0 to 1. And v is going to go all the way around. So there's a nice parameterization of the surface. We're ready to go now. Same thing. We want to compute the integral over the surface of xi ds, like that. All right, so let's do it. Let's do r sub u. R sub u, let's again remind everybody where the u's are. They are sitting here, here, and here. So we take the partial with respect to u, we get cosine of v, sine of v, and 2u. R sub v, where are the v's? The v's are sitting here, here. So the partial with respect to v is going to be minus u sine v, u cosine v, and 0. Now we're ready for the cross product. The cross product, we get sine v times 0, nothing, minus 2u squared cosine v. The middle component is going to be 0 again, 2u squared sine v, but another minus sign from the middle coordinate, 2u squared sine v. And then last, u cosine squared v plus u sine squared v, which is just u. Doing that Pythagorean identity simplification behind the scenes. All right, we do need, in this case, the magnitude of RU cross RV. That's going to give us 4u to the 4th cosine squared v plus 4u to the 4th sine squared v plus u squared square root. Let me give myself a little more space. There is a Pythagorean simplification here, right there. So let's do that simplification. 4u to the 4th plus u squared to the 1/2. And it looks like we can pull a u squared out of this thing as well. So let's do that. U 4u squared plus 1 to the 1/2. And you again might wonder, I'm taking a u squared out of the square root. Where's my absolute value? Notice up here that the parameter range is over a positive set, and so we don't need the absolute values. We now have the magnitude of the cross product. We're ready to finish building this integral. The integral, let's do u first, 0 to 1, and then v, 0 to 2 pi. The integrand is z, and we want to evaluate it at along the surface. So in this case, z is equal to u squared, so we get u squared, and then times the magnitude of ru cross rv, so that's another factor of u, and then 4u squared plus 1 square root, and then du dv. There's no v component here, so we can immediately write this as 2 pi times the integral from 0 to 1 of u cubed 4u squared plus 1 to the 1/2 du. This is a trig sub, and it's probably going to be a pretty challenging one, so I'm jumping over to Sage here, and I'm going to get, based on Sage, pi over 60 times 25 root 5 plus 1, which is approximately 2.98, and that's the mass of this surface with the given density. That's the mass of the surface. Positive number, right? We need a positive number here, otherwise it doesn't really, that's a big clue that you've done things correctly. All right, moving on to 304, another flux integral, this time over the closed surface, x squared plus y squared plus z squared equals 1. Now, you can see my comment here. This belongs in section 6.8. I'm going to discuss this, I'm going to set it up, but I'm not going to evaluate because it's actually ridiculously challenging to compute until you learn the divergence theorem in 6.8. So it's a good exercise to set up, but don't try to evaluate. All right, how do we parameterize a sphere? You guessed it, we're going to use spherical coordinates, and rho is going to be the constant function 1. So a parameterization of this surface in u and v is going to be cosine theta sine, u and v. Cosine u sine v, sine u sine v, and last not least cosine v. Playing the role of theta is u, playing the role of phi is v. Whenever you write down a parameterization, of course we want to write down the range of the parameter. U playing the role of theta and building the whole sphere, u is going to go from 0 to 2 pi. And v playing the role of phi, again covering the entire sphere, is going to go from 0 to pi, from North Pole to South Pole. All right, you've seen this once, so let's go over to Sage and see how to do this kind of computation on Sage. So we'll write, let's declare the variables first, u and v, and then let's write our parameterization as a vector, and we have cosine u sine v, sine u sine v, and then last cosine v. And then let's just show our, so that we're confident that we've put things in correctly. There they are. Let's compute r, the derivative of r with respect to u, and the derivative of r with respect to v. And let us just show those, ru and rv. That looks legit. Right, we see the 0 there in the z component on the u derivative. So all of this is stuff that looks like stuff that we did in that previous calculation, so we should feel good about that. Let's get our hands on RU cross RV. That's RU dot cross product with RV, and then let's simplify full and show RU cross RV. All right, so there's RU cross RV, nicely simplified. Now, that's where we stop. We don't need the magnitude of RU cross RV because this is a flux integral. So we've now found n. In this case, n is this vector. That's n. We also need f of r. So we need to evaluate this nasty function up here, f, along the surface r. So everywhere we see an x, we use this. Everywhere we see a y, we use this. Everywhere we see a z, we use this. This is hideous. This is just crazy. But let's kind of work our way through it. So we have 2 times y times z. So 2 sine u sine v cosine v. That is the I component. Then we have the arctangent, and honestly, I'm not even sure whether the z is inside the arctangent or not. I'm just going to assume that it is. So we have tan inverse of the quantity x cosine u sine v times z cosine v. And then the last component is e to the cosine u sine v y sine u. And then what are we supposed to do? We're supposed to dot this with n. And you can just see that this is getting worse and worse. I guess just for the heck of it, let's see if we can pull this off in Sage. So let me build f. F is the vector 2yz arctan of xz, and last not least the exponential of x times y. And let's show f just to make sure that we've got things correct. Oh, the y, x, y. I forgot to define x, y, and z. Var x, y, z. There we go. Now let's substitute the components of r into f. We can do that. Let's call this f r, f evaluated at r, and that is f substitute in the first component, or not even in the first component, throughout we want x to equal the first component of r, which is denoted r0. We want y to equal the second component of r, which is denoted r1, and finally z to be the third component of r, r2. And let's see what that looks like. Oh, I vaguely remember this. The vector doesn't want a list like that, so I have to kind of separate them out into. I think this will work. There we go. All right, so that's what that looks like. Now, what if you wanted to dot that with RU cross RV? We can do that now. So let's do FR, I'll just call it dot product. Running out of variable names here. So let's do the dot product of FR with what? RU cross RV. And let's just simplify that as much as we can. And let's show that. Okay, and now you're supposed to integrate that, right, over the entire thing. And I think just for the hell of it, let's copy this into the worksheet just to show you how absolutely hideous this really is. All right, so this is what we get when we look at f of r dotted with Rn. And what are the limits of integration? Remember that u is going from 0 to 2 pi, and v is going from 0 to pi, and then du dv out there. Any of you want to try your hand at that integral? Have at it. I'm done. I'm pretty sure Sage can't do this either. We will find in section 6.8 that the divergence theorem can actually let us do this, and you get very simple results there, which is the true power of the divergence theorem. So that's set up. Oh, and I guess there was one other item that we should talk about. This is a closed surface. Did we actually use the outward pointing normal? This is a challenging question to ask also. And all you really have to do is, since the sphere is what we call an orientable surface, and since this parameterization describes the entire sphere, we really only have to test this at one place. So to test whether this is the outward pointing normal, sketch the sphere like this, and just pick a point on the sphere and see which way this normal vector is pointing. Is it pointing in this direction, or is it pointing in this direction? Which way is n pointing? Well, what are the parameters that correspond to this point? They are u equals 0 and v equals pi over 2. So we can get an idea about which way n is pointing. Is it pointing inward or outward simply by evaluating n at the point u equals 0, v equals pi over 2. Let's go do that, and I think we can do that in Sage. We've got our n here somewhere. Yes, it's RU cross, it's what we're calling RU cross RV. I could have all called it n. And let's evaluate RU cross RV. RU cross RV subs, and let u equals 0. And then let's also substitute v equals pi over 2. And we get the vector negative 1, 0, 0. Negative 1, 0, 0 is pointing along the negative x direction, right? So it turns out that we're dealing with this vector right here. That's the n that we're getting. That's inward. And you never know in advance when you set up your parameterization, you never know whether RU cross RV is going to be inward or outward. You have to test it. So I tested it at this point. I see that it's pointing inward, which means I better introduce an overall minus sign if I want to get the right answer. So this makes it outward. So that's the tweak. Now, you might be saying, hey, Schuler, why don't I just plug in the North Pole here? Wouldn't that be simpler? Because then I've got u equals v equals 0 up there. I'll say, all right, let's try it. Let's try it. So instead of u equals 0, v equals pi over 2, let's do u equals 0, v equals 0, and plug it in. And we get 0, 0, 0, and you're like, holy crap, what vector is that? And it turns out, no vector, right? You get the 0 vector when you plug in that point. Now, here's where we learn a little something about the spherical parameterization, or using the spherical coordinate system to parameterize. This is technically not a smooth or regular parameterization because RU cross RV is 0 here. RU cross RV is 0, is the 0 vector here. So this is not smooth, aka regular. And you're like, well, can we do any of this stuff if it's not smooth or if it's not regular? And short answer is yes, because it's only misbehaving at one point. And integration is very forgiving about misbehavior at one point. So just stay away from that point if you want. If you really want to get technical, do the surface integral and just stay away from the poles. I'm not even sure if both poles are a problem. Let me check the other pole. So at the other pole, we could take, say, u equals 0, and we could say v equals pi. And yeah, the other pole's a problem too, but everything in between is fine. So what you can do is just kind of do the integral from really close to the North Pole all the way to really close to the South Pole. That would involve just backing off a little bit here, minus epsilon here and plus epsilon here, and then take the limit as epsilon goes to 0, and you'll get the same thing. So it turns out that this smoothness, this regularity thing that the book talks about, spherical coordinate systems fail in this requirement, but they're okay because they only fail at single points, and the integration is kind of okay with that. This is well outside the scope of the class. I just want to let you know that it's okay for these things to kind of fail at a single point. In most cases, you can still conduct these surface integrals. Okay, I'm going to pause and get a drink here. Hold on. Testing, testing. All right, we're back. Next one, 310, we want to evaluate the surface integral. This is just a scalar surface integral. I thought it was interesting because it's the way that the surface is described might be a little bit challenging, so let's just play around with it a little bit. So S is the part of the plane x plus y plus z equals lambda that lies in the first octant. So if we give ourselves a bit of a sketch here, do a better job on the y-axis there. Okay, let's look at where this thing strikes each of the coordinate axes. So here's x, here's y, here's z. We can see that this is going to strike the x-axis at lambda, it's going to strike the y-axis at lambda, and it's going to strike the z-axis at lambda. And if we connect the dots, we get this little sort of tetrahedral kind of volume, and then the surface that we're interested in is the top. There's S. All right, how are we going to parameterize this? Well, this looks like a job for good old Cartesian coordinates. We'll just figure out the domain of integration in the xy plane. So let's look at the xy plane. And what we see, here's lambda, this is x, this is y. This is lambda, and up here is also lambda, and we're looking at this little chunk here. And we're just going to let x and y range over this, this space. So x is going, let's do vertical slices. So x is going to go from 0 to lambda. Y is going to go from 0 up, up to this line. Well, what's the equation of this line? You can kind of look at it. The equation of this line is 1 minus x, sorry, not 1 minus x, lambda minus x. I can see that if I plug in x equals 0, I get lambda. If I plug in x equals lambda, I get 0. So that describes the equation of the line. So what's y doing? Y is going from 0 up to lambda minus x. So that's the parameter range. What's z doing? Well, we can figure that out from the equation here. Solve for z. Z is equal to lambda. having trouble with my lambdas today. Lambda minus x minus y, like that. And we're ready to build a parameterization. R of u and v. U playing the role of x, v playing the role of y, and up here for z, lambda minus u minus v. And what's the parameter range? 0 less than or equal to u less than or equal to lambda, and 0 less than or equal to v less than or equal to lambda minus u. That's the parameter range, and we have now parameterized the surface. This is a scalar surface integral, so we can just go through the whole process of RU, RV, and so forth. Let's do RU. RU is 1 and 0 and negative 1. RV is 0, 1, and negative 1. Let's see what RU cross RV is. RU cross RV, we're going to get 1, 1, and 1. 1, 1, 1. Nice. What's the magnitude of that? Square root of 3. And we're nearly ready. So now we build the surface integral. Let's integrate with respect, well, we kind of have to integrate with respect to y first because there's an x dependence in that direction. So we're going to go from 0 to lambda minus x, and then we're going to go from 0 to lambda minus u, and then u is going to go from 0 to lambda, like that. In the integrand, y is v along r, and z is lambda minus u minus v, lambda minus u minus v. And then don't forget our square root of 3, and then dv du. Took the liberty of plugging that into Sage, and I get the square root of 3 over 24, lambda to the 4th. So remember, lambda was this parameter that just kind of controls where the surface is, and that's how this integral depends on lambda. Okay, in 3.16, we're asked to use geometric reasoning to evaluate this integral, where the surface is x squared plus y squared plus z squared equals 4. All right, now, if we're going to integrate this thing on the surface x squared plus y squared plus z squared equals 4, we immediately know that this integrand is equal to what? It's equal to 2, the square root of 4. So we know that this is the integral over the surface of 2 ds. The 2 can come out, and now we have the integral of s ds, and that just is the surface area of the sphere. And we actually have a formula for the surface area of a sphere. It's 4 pi r squared, where r is the radius. In this case, the radius is 2. So 16 pi is the answer, and we didn't have to lift a finger. We just did a little bit of geometric reasoning. All right. The last one, let me check my notes here. Gosh, I feel like I've done this a lot. I think the interesting part of this one is perhaps the fact that there's a massive typo, and then the fact that the surface is described in an interesting way. The massive typo is this. I think, yes, it's this. Just drop this whole first sentence. And then start with, let S be the spherical shell centered at the origin with radius A. That's this piece here. Let C be the right circular cone with a vertex at the origin and an axis of symmetry that coincides with the z-axis. That's this bit here. Suppose the vertex angle of the cone is phi naught, where phi could be any constant between 0 and pi over 2. What is the vertex angle? It's this angle between the side of the cone and the z-axis. That's phi naught. All right. Determine the mass of the portion of the shape enclosed in the intersection of S and C. Enclosed in the intersection. So that's kind of this piece in here. All right, so that's how the surface is described. How do you want to parameterize this? I would suggest spherical coordinates because the surface is actually a part of the sphere. So we'll use spherical coordinates to write R of u and v is the vector, and then we trot out the usual spherical coordinate transformations. What's the radius of this sphere? Because that's going to determine rho. In this case, it is, where is it? It's radius a, so rho is a, and we have a cosine u sine v, a sine u sine v, and then finally we have a cosine v. Now remember, u is playing the role of theta in the spherical coordinate system, so it's going to range around the entire z-axis. And v is playing the role of phi, and it's going to go from 0, the North Pole, out to the cone, which is the angle phi naught. So there are the limits of integration that we'll eventually want to use. Let's, just because you've seen this a few times now, let's jump over to Sage and do this calculation there. So let me get my hands on the variables a, u, and v. Let me specify also, just because Sage might find it useful, we'll assume that a is greater than 0 because it's the radius of that sphere. And then let r equal the vector a cosine u sine v, a sine u sine v, a cosine v. And you know the drill, right? Ru is equal to the derivative of r with respect to u. Rv is the derivative of r with respect to v. Ru cross Rv is Ru dot cross product with v. And then let's simplify this as much as possible. And then let's show Ru cross Rv. Okay. That needs to be Rv. Okay, there you have it. That is Ru cross Rv. Let's now compute the magnitude of Ru cross Rv. Yes, that appears to be what we're doing. So let's say, I don't remember what we're calling this now. Let's just call it ds for lack of a better term. ds is going to be Ru cross Rv dot norm, and simplify this as much as possible. And then let's show ds. Okay, so Sage is worried that the sine squared could be negative, so it's just showing you the square root of sine of v, but we can simplify that to just a squared sine v. So doing all of this work, the magnitude of Ru cross Rv is just a squared sine v. A squared sine v. Good. All right, we're ready to do the integral now, and we have to invoke the density function delta. That's a lowercase delta right there. Everywhere you see an x, use this. Everywhere you see a y, use this. Everywhere you see a z, use that. What the heck? We could try substituting those in as well. So delta is equal to the expression x squared, y squared, z. And we want to substitute into delta. We want x to equal r0. I think I can use commas here because this is not a vector. r1 and z is equal to r2. And I want to simplify that. As much as I can, and let's just store that in, I don't know, let's call this delta r. So it's delta along r, and then we'll show delta of r. And there you have it, a to the fifth cosine squared u, sine squared u, cosine v. Okay, it's a train wreck. And then we could multiply that by a squared sine v. All right, so let me build the intermediate integral for you. So now we're going to integrate in the u direction from 0 to 2 pi, in the v direction from 0 to phi naught, a squared sine v times the quantity. Let's make this a little bit smaller here. Drag it up to where we want it. Nope, it's not going to let me drag it up there. So annoying. Okay, so put this right up here. And then we're integrating with respect to u first, and then with respect to v. Again, another nasty trig integral here. Let's see what Sage has to say about it. So we'll integrate twice. And we're going to integrate delta r times a squared times sine of v. And we're going to integrate in the u direction from 0 to 2 pi. And then we'll integrate in the v direction from 0 to, oh gosh, phi 0. And it's going to complain about phi 0 because I haven't declared it yet. Let me declare it. And then let me also just assume that phi 0 is greater than 0. And let's store the result here, just call it result, and show the result. And we get this expression, pi over 24, a to the 7th sine of phi 0, sine to the 6th phi of 0. So yeah, that looks like a really fun integral to do. And we'll just put that right there. Maybe right here, I don't know. Or maybe down here. Oh God, giving up now. You get the idea. Okay. Yeah, so that's it. A lot of these integrals are really hard, so you might want to jump over to Sage. But it's good to do them kind of by hand too. There were a lot of errors in the exercises here. I've tried to summarize them here. and you can pause and have a look at these. I'll also put these notes in the Canvas discussion. Go have a look at that, work on some exercises, and when you're ready, go hit the web work. Thanks. Bye.